All right, welcome back to the Design a Computer from Scratch series. This is part 5, and in this part we will design the ROM for the program, the CPU's ROM. Along the way we will have to figure out how to create the ROM file, and that's where it's going to get a little bit fun, but bear with me. As a refresher, what do we know so far? The ROM contents have to be created, but Altera has a ROM wizard, and unfortunately it requires the ROM contents. You can't just not have contents for a read-only memory. It needs contents. So that's going to be a little bit of a challenge, but with our instruction set design we can overcome that quite easily. The ROM has registered address inputs, so we have to remember when it comes to the control and timing section that's going to add a delay between when we have the address present at the ROM and when the data comes out from the ROM is 1 clock later. So we could do stuff to load it a clock earlier, not worth the effort. Branches make it much more complicated to pre-calculate that, and it's just it's fine. It'll affect the performance by 1 clock, but not a big deal really. In the general scheme of things, 12.5 MIPS is pretty darn good for a little CPU, tiny little CPU. The complication I mentioned is the ROM initialization file. In Quartus, you can give it either an Intel hex file or an MIF file, memory initialization file, to fill up that ROM. And hex files are complicated. They have checksums. Yeah, there's utilities to create the hex file from a binary file or do other things like that. But the Miff file format is really simple, and it should be fairly easy to take our assembly program and convert it with a little utility, and we'll take a look at that here. But the output of what we'll do is a Miff file, which you will select when you configure the ROM, and we'll go through those steps. Example of what the Miff file looks like. As I said, it's pretty simple. The dash dash is comment, similar to VHDL format. Depth is how many words you're writing or will be reading from the ROM. In this case it's 4, 1, 2, 3, 4. The width is the data width, and what we're doing here is all 16 bits. And you can see we have what looks like a no-op instruction. I haven't talked about that yet, and then a couple other instructions, and then a branch instruction here. But this is sort of an example of one. Looks like it's going to branch to address 1. The address radix, well, we're just going to count in decimal because it's a lot easier if you're counting in decimal to correlate what you see in the ROM file to what you see, or in the Miff file to what you had in your source file. The data radix is hex, so these are all hex numbers. You can see there's a hexadecimal digit there. And really it's a content begin and end statement. Again, very much VHDL looking with semicolons at the end of each of the lines. And the format here is the address 0, colon, and then the data values of the 4 data values. But what we need to create this file is some sort of an assembler. And I've written one in Python that we'll use to do this. If you don't have Python, it could be easily created in almost anything else. I think it could probably even be created in Excel, but I didn't do that. I just did it in Python 3, which is what I have. That assembler will take that source file and convert it into a MIP file, and it will encode the opcodes. So the thing we have to do at this point that we've avoided to the point, because we haven't touch the actual encoding of the instructions, is to look at how the opcodes are encoded. LRI is load register with an immediate value, shown over here in the description. We'll encode that as a 0010 or 2 in hex, and the next 4 bits are the register number, and the next 8 bits are the immediate value that get loaded into that register selected by the register number. I/O read and write are very similar to each other. 6 and 7, again, we have big gaps in here to add other instructions, and we're leaving plenty of room This is coded to be compatible with a predecessor processor I had. And these could be set to anything as long as the VHDL code that decodes these maps the same function to the same opcode bits. But IO read and IO write take either a register and read from an IO address, that 8-bit IO address, read from it into the register. That's what an IO read does. An IO write takes the register that's selected and writes it out to an IO register. The only ALU function we're going to implement at the moment is ARI, which is coded as 10008 in hex. And that takes that register number and ANDs it with an immediate value. So if you've read a status port on a UART into R0, you would do an ARI to AND 0 with that immediate value of 1. Let's say if you're looking at the is data receive ready. The other 3 instructions we have to do with flow control. The first 2 here, address or opcode C and opcode D, are branch on equal to 0 and branch not 0. We haven't implemented any of these yet, but we're setting ourselves up, and we will need these to create the ROM file. So we're sort of pre-creating them right now. The branches and jump all have either the offset, which actually this shouldn't be offset. This really should be the address that it's going to go to. I had an offset before in the previous generation processor, but it had to do math to add the offset to the current address, and there's really no value in that for 12-bit address because we're not going to be branching within pages. We're going to always be going to some location that's known. So that's branch of 0, branch of not 0, and jump to an address. So that's our entire opcode coding, but as you can see, again, there's quite a few empty spots here. 0 and 1 are open, 2, 3, 4, 5 are open. There's other spots that are open in these 16. Of the 16 possible opcodes, we've only got 8 encoded so far. So room for 8 more opcodes without doing anything to disturb the simplicity of this mapping. So the assembler is a 2-pass assembler. The first pass goes through and looks for labels, and the label is either the addresses here or it's the location of that instruction for the case of branches. And that first pass will build that symbol table. That symbol table will be used in the second pass to set the values for those symbols. Picked a very, very constrained format, but it should be available on anybody that's got Excel or LibreOffice Calc or anything that's an open office type product as well. CSV is a very common format, very widely available, and I've very tightly constrained what can be in the columns and such. And that constraints include the use of a very specific header just to make sure you got the right kind of file when it reads it. But it'll read it in and break it up into what it needs to be. Now my assembler is written in Python 3. It's not very complicated. You can see what it would have to do from the previous slides. It's a tkinter Windows app, so you double click it and open the file. It saves the path of where your last compilation was done to make it a little bit easier to run. And it does produce 2 types of output files. One of them is the Miff file, the memory initialization file, which is used by the ROM itself, and a listing file to make it easy to debug. It shows it adds the addresses to the source file and creates a separate listing file. The source file, this is a very simple example of the source file that just jumps to start and starts itself. Every line has to have an instruction on it. Labels can't be on a line by themselves. If you wanted a label on a line by themselves, you could probably throw a no op in there and do that, but it really serves no great purpose to do that. The first row here is extremely tightly controlled. It needs to be label, opcode, reg underscore label, off score underscore address, score address, and then comment. And that will be, since it's so tightly constrained, it makes the parsing very, very simple. Everything is in a CSV, comma, separated values list. And if there's nothing in that first spot, it's not a label. If it's a jump, look here for a label. If it's a jump, there shouldn't be anything in an offset. If there's a comment, then keep track of that comment and put it in the list file as the output. To run the assembler, it's located in the GitHub, which I think there's a link for at the end of this video. Double click on Pi assemble for CPU 001. I need to change the label up here, but it's the same as my other processor. I just changed a few things in it, so it basically runs. You do File, Open, and browse over to where your file is, and you select it. In this case, we're going to look at Part 6, Test 1. Probably should have been called Part 5. I lost track of what parts I was on. But it's located in the same place the CPU is, but in a folder called CPU code. And all the examples will be up in there. I might try to fix those descriptions. Bad, then it won't match the video. I'll just leave them alone. But this has an example that we can run. You run the example, or run the assembler. It will print out a message. Probably should be an info box, not an error box, but it'll come up and say complete. You hit exit. If there was any errors, you type something wrong, you got the wrong opcode that isn't supported, you did something wrong, it'll print a message over in your command window to tell you what the error was. It'll print the line itself that the error occurred on, not the line number necessarily, but the instruction, and try to give you a hint as to what was wrong. It's not a sophisticated program. It could be replaced with a piece of Java code, or somebody wrote something in C or anything else. Let me know and we'll commit it up if somebody wants to make a true executable for people that don't run Python. But I'm of the religion that everybody should be running Python for most of what they do. The output list file is just a text readable file, and I'm running Notepad++ to look at it. It has the address at the beginning, it has that label, it has the encoding of the opcode. A jump is E000. It's going to jump to start back to location 0, and this particular piece of code loops forever. It's all tab separated. It produces decent format. If your labels are 6 or 7 characters, you're fine. If they're longer, then the tab separated output might look a little messy. It's, again, not very complicated, designed to be fairly simple and easy to use. Miff file that we just made, very simple as well, conforms to what we had before. Did change the name of the program on the output, so it does say, hey, well, this was generated by PyAssemble for CPU 001.py. Again, up in the GitHub if you want to play with it. If you want to make it better, feel free. If you want to make it better enough and you want to let me know, I'll commit it up to the site. But basically, it's going to put that same information. So depth is 1. There's only one thing in here. It's a 16-bit thing. The address radix is in decimal, not hex or octal or anything like that. Data is in hex. That's an E000. Content begin and end, and a bunch of semicolons on everything except for the begin. Doesn't have a semicolon because it's terminated by the end down here. Well, now we actually have a ROM initialization file, and it's got almost do nothing code, but it does sit and loop on itself. So that should give us a good test bed for checking stuff. To load that, it depends upon the version of quarters you're using, but in 20.1, which I'm using, it's under the IP catalog, which can be found under Tools. So Tools, then click IP catalog, and it pops up this little IP catalog window. I had to drag it around to get it where I want it. But click into Basic Functions, On-Chip Memory, and ROM, and when you want the one-port ROM for what we're doing, but there's other choices here as well. Select VHDL for the type. You want to stay consistent. If you want to stay consistent with what we've done before, keep it in VHDL. And I'm going to call that ROM underscore 1kw1 kiloword.vhd is the name I'm going to put on it. Probably didn't have to put the ROM 1kw, and it does sort of mess up things if you change the name of it, but this process is really pretty simple to create that ROM. So I think this will work just fine. But that is what I did. The size could be different, as we noted, 12 bits of address. So that's actually 12 bits of word addressing, which is 4K, which is a pretty darn big file for a fairly simple processor. Nothing I've done, even done some complex things with this processor. Nothing used more than 512 locations in what I've done. And most of them have been 10 or 12. Next step in the catalog, IP catalog wizard, is to set the address and data size. And note here that there's something we really don't want, and that is that the output is clocked as well, and we really don't want or need that because that would add an extra delay to our clocking scheme. We really can just have it, but that's not able to be set on this screen. It's set on a screen that comes up later. The thing you want to do here is set the bits, the 16 bits. And while we're here, we could take note of something. These parts that are used inside of here are these M9K. So they're 1K of 9 bits. We could easily design a processor with no extra resources used that was an 18-bit processor. Chosen not to do that. It's a little more compatible with some of the other FPGAs that are only 8 bits wide. The 5 series, Cyclone 5 series, has 10-bit wide. You could make a 20-bit wide CPU and expand the field. If you wanted more instructions, you could throw a bit or two on there for that. Even with this Cyclone 4, if we had 18 bits, instead of having 16 instructions, we could easily have 64 instructions and just pick it out of this fact that we've got a 9-bit here. And of course you'd set that to 18, but for what we're doing, we're going to leave this at 16. And we determined we're going to have 1,000 words, so that's the 1024. Both these are pull down, so you pick that. And as you progress through this wizard, it updates the little symbol to show you what you chose to do. Now this is the screen where you would unclick that Q output port, and notice that output register has disappeared, so it's not there anymore. We don't want to have any of these other buttons click. We don't need a read enable. We just wanted, if you put an address on here and it's clocking at every CPU clock, if you put an address on here, the data is just going to come right out and stay out. We don't want to slow anything down. This particular screen is the one where you go in and pick the file that you created, that Miff file. The one thing that's not obvious is, hey, you can browse to it. You go, oh, it's not there. Well, the default for type of file here, and I wish Quartus had both defaults because they're both legitimate options, but the default here is hex. And so you have to click this types of file and then select the Miff, memory initialization file. Once you do that, it'll pop up in a list, and you double click on it and select it, and then it'll populate it here in the file name. The last step is we want to add it to the project we're on, and so that comes up pre-clicked. I'm not adding it to any other projects, it's just on this project, so clicking that button on and this button left off is what we really want to do. But that'll add it into our project in the files list. The ROM, if this is set to files in Project Navigator, the ROM will now appear up in there, and if you click on that little arrow, it'll show the VHDL entity for it, and we get to see what the pins are named inside of it. Double click on it to get it to open. The ROM pins list from that file was ROM 1KW is what we underscore 1KW is what we called it, and it's an address, a clock, and a Q. I hate that order. I wish the clock was first. So when we grab it, we're going to grab it and turn it into our usual stripped down version of it, add ROM to it, and we put it in our CPU 001 entity. We're going to add the work dot. Don't forget that. Don't forget to add your map. You don't need this part, this nROM 1KW after. It'll just confuse it. But this is what we paste into the unit that goes above it. Pretty simple. ROM is just, hey, clock every clock. It's a synchronous interface to it because it'll latch up that address, and then the data comes out after it. And this is an extra typo there we don't need. So let's connect that to what we have done so far. In fact, we're almost already there with what we have. We have to only add one signal, which is the ROM data, and that's the instruction that's actually running at the moment. And it's a standard logic vector, 16 bits wide like we've done before. The ROM entity in the top is going to be defined as on the previous slide. The things we want to hook up are the clock. We're going to hook that right directly up to the 50 megahertz clock. The ROM has no problem running at 50 megahertz. The fact that it's clocked holds everything for us through the cycle, so as soon as the program counter is there and ready to go, we clock it on the next clock. So it's plenty of time for it to set up into the ROM. The address is that program counter, because that's literally what's driving it, is the program counter. And the thing to keep track of here is, even though we had a program counter that was 12 bits, we're only using 10 of those bits because we only have a 1K ROM here. If you had a different size ROM, this number would be different. And the Q output from the ROM, the data out, goes to ROM data. So now we're fully connected and we're driving the ROM into the part. Let's test it with our single instruction. We're going to load the PC with 0, and we're going to simulate a jump. It shouldn't do much on what we look at, but it should do something. And simulate jump, and we can select here the D0, or select D15, D0 with key 0. So what this is going to do is look at the most significant bit out of the ROM, and again, the ROM value we expect at location 0 from back here. The ROM value we expect is way back here, is E0. So the most significant bit's high and the least significant bit's low. So if we're toggling with our key between the most significant and least significant, we should see the light toggle. So yet again, we're using the button, using the LED to verify that the ROM contents are being read out. And that's exactly what this function right here is doing. So if you press the key, it'll pull the 15th bit. If you release the key, it'll pull the 0th bit. And pressing the key turns off the LED, releasing turns it on again. Remember, the key is flipped, so it works just like it should. Again, not a rigorous test. We're not putting a bunch of different values in it and seeing if it works, but due to the way these things are designed, if you get one bit of the thing working, your likelihood that another random bit inside of it's bad is pretty close to 0. So what did we do in this video? Well, we did a lot that you didn't really see, but we basically encoded the opcodes into the bits that we want to have for the particular instructions. What you didn't see was writing the assembler. Source code is up there, of course, because Python is source. And we wrote a simple test to jump to ourselves. We assembled that code, and we created a ROM entity with that assembly output, loaded it as the Miff file. And we did some minimal testing, enough to convince ourselves that the ROM is accessing and reading out constant data. We didn't change the program counter. We didn't run through any program. Didn't look at that change, but we'll do that as we move along here. As in the last video, there's a check-in for this. Again, this is misnumbered by the video number. I got lost in my numbers, but I'm going to leave it that way for the moment. This is a branch of what the progress is up until this point. If you just want to play with what we have and replicate it, the top level entity is still in the same place, and the GitHub repository root is back here. I'm creating branches for everything that's worth playing with, starting from the past video on, and that should help quite a bit for playing with it. You don't have to do all the typing, but if you want to play with what it is, it's up there and can be downloaded. Just select the branch inside of GitHub on the internet, and that's really about it. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindy where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.